Hello everyone, this is Pankaj Chaudhary from cbpsecrets.com. Today we are going to discuss C++ STL containers. So we are going to discuss all the STL containers which present in C++ and what is their use along with their properties. Okay, so C++ is providing lot of containers like a vector, list, map, set, etc. So you are having multiple number of containers. So among these containers, which one is the best one, and based on your requirement, which one you need to choose? This is one of the difficult question in STL. Okay, because these all containers present available in C++, and C++ engineers developed all type of containers for your requirement. Now so before choosing these containers, before choosing these appropriate container as per your requirement, you must need to familiar with the containers, what is their properties, for which purpose these containers has been implemented. Okay, then only you are able to decide which container you are going to use based on your requirement. Okay, so we are going to discuss just in summarized form, and we are going to discuss all the STL containers, okay, their properties and for which purpose it is designed. Okay, then we will take one example, and based on the example we will actually try to find search the appropriate container based on your requirement. So I will provide some requirement, and then we will choose the which container will be the correct one. Okay, so first container is, so before going to container, we are going to just see all the STL containers are divided into two parts. The first one is the sequential container. And another one is an associative container. Okay, so sequential container means the data which is stored in the container is placed in the sequence. Sequence means that means the order in which you are going to insert the element into the container. So in the same order it will store. Okay, so container is not going to change the order of your data. Okay, that is the sequential container. So an associative container is something, the order of the element will be changed. So if you print some of the associative container, you cannot it will not print the same order in which you are going to you are inserting data into the container. That is associative container. Okay, so order in associative container, order is going to decide by the container, not by the user. So that is the associative container. Now I will first describe this as sequential container, then I will move to the associative container. So in sequential container we are having two parts. The first is the consecutive memory allocation. Okay, so in sequential, the example of sequential container is vector, list, decube, queue, stack. These are the part of the sequential container. So if you are having a vector, okay, and you have inserted the element like 11, 22, 33, 44, and if you print this vector, then output will be same, in same order in which you have inserted this data into the vector. So output will be like this: 11, 22, 33 and 44. Okay, the same behavior you can see in the list as well. Okay, so if this is the list and you have inserted something like 11, 22, 33 and 44, if you print the list, you will get the same the data will come in the same order in which we have inserted into it. That is the sequential container. DQ is again same, Q is same, stack is same. Okay. So here I have this SQL container divided into basically two parts. So consecutive and non-consecutive. Consecutive, that means so memory of each element is consecutive. Okay, so each element is stored consecutively. So like as in vector, if you talk about the vector, so elements are consecutive. Okay, it's sequential then plus consecutive. So let's say it's stored something like 11, 22, 33 and 44. So in this case, so 22, it's 22 came after 21 only. Okay, 33 came after 22, 44 came after 33. So this data is stored in the consecutive manner. Okay. So in this case, this type of containers, consecutive sequential container is having support of the random access. Okay. So random access is something, you can access the element by the index. If you talk about the list, in this case element is, its memory is not consecutive in this case list, because if some node is present here, then another node is present here. So this memory is not like this. This is the 101 and this will be the 102. This is not going to happen in the case of list. Okay, so this memory is placed somewhere else, and this memory is placed somewhere else, and this node is pointing to this node. Okay, this is the behavior of the list. We are having associative container. Okay, there are two popular examples of the associative container, is a map and set. Okay, so if you talk about these sequential containers, okay, so this is completely the sequential container, like this vector, list, these all are things, all are the part of the sequential container. If you talk about the map, map is associative containers. So before moving to the properties of the map and set, we first just go little bit about data structure. Sorry. So we are going to just a little bit discussion about regarding the data structure. In data structure, if you talk about the data structure, as we know that we are having multiple data structures. Like a data structure is something, so let's say you are going to manage the data. So in data structure we are having concept of array, okay, list. So these are the basically they are like as we have queue, stack, all the things. These are the sequential data structures. Okay. Now in this type of data structures, so the the advantage of sequential data structure is insertion and deletion is quite very simple. Okay, if you talk about the list, in list part, insertion and deletion is very simple. It's having less complexity. Or if you are inserting in the into the middle, that case is different, because before inserting into the middle you have to travel. You have to traverse from the start or end to that location. Okay, but if you are going to insert some data at the beginning or at the end, that is having the less complexity. Okay, or you can achieve it in amortize big of one complexity. This type of, but in the major disadvantage of sequential container is searching. Searching is one of the problem which is present in the sequential data structure. So if you are having sequential data structure, and if you want to search something into it, so you have to travel, you have to traverse on complete data structure, complete list. Okay, so it will take, the complexity will be like as big of n. Okay, so it will take n complexity to traverse on the complete list. So searching is it's costly operation in the sequential data structures. So for this, engineers came to the associative data structure. So in associative data structure we are having concept of binary tree. Okay, so binary tree is another data structure which is having it's in the binary tree, the searching is less costly than the sequential containers. Okay, So as we know that binary tree is having concept of, you know, every node is having 0 or 2 child node. This is the concept of binary tree. Okay, so every node is having child node of 0, 1 or 2. So between 0 or 2. So if you talk about this is the binary tree. Okay. Now in binary tree there was having some disadvantage because you know, binary tree is not balanced. So how this complete data structure is implemented? So when you are having concept of binary tree, so then on the binary tree people started to apply some of the balancing algorithm there. So when they here they applied BST, binary search tree. Okay, so over the binary tree, so binary tree is a base a base concept. Okay, and on the binary tree we have added another feature. Okay, so binary tree concept is present here in the BST, and we have added another rule in the BST that left side child will be less than the root and right hand child will be greater than the root. Okay, so if this here 11, then here 9, here will be 12. Okay, this is the BST, binary search tree. Okay, so binary search tree is when you know, engineers achieve this binary search tree, then searching becomes quite easy. Okay, now it is also having some disadvantage, because in some of the cases, like as let's say the binary tree like as 10, 9, 8, 7. Okay, this is the one tree. Okay, so this is following the BST, but in this case this is the complete one chain. Okay, so this BST is nothing, it's like as a sequential container. Okay, so in this BST, again in this BST the searching is costly. Okay, so BST was not the perfect one. Then people started new tree here, that is the Avl tree. Okay, so Avl tree is again a binary tree only. Okay, so in Avl tree is again a binary tree. So Avl tree, so Avl is again you know, it is having some balancing algorithm. Okay, so because in the previous example we have seen that, so the BST is like as BST becomes the sequential container in some of the cases. So because, you know, so for this to resolve this type of problem, we came to the Avl tree. Avl tree is saying that, so at every node the distance of the left or right should not be greater than 1. Okay, it should be -1 or 1, 0 or 1. Okay, if you subtract left from right or right from left, so it should be like this. Okay, so this is giving some little bit, you know, guarantee that your tree is not unbalanced, it will balance properly. Okay, so if tree is properly balanced, then searching will be less costly, searching will be optimized. So this is the concept of Avl tree. It's having some you know, balancing algorithm like as RR, right rotation, LR, RL and LL rotation, something like this. Okay, so this was having some concept. It is also again Avl tree is having few disadvantages, like as rotation is quite complex in Avl tree. Okay, then people we came to the red black tree. Okay, so Avl is also again Avl is also binary tree, and here this is the concept of red black tree. Red black tree. So red black tree is having some own principle, like as every leaf node will be red, their node red combination like this. Okay, red black tree is so our aim is, so these all trees, what our aim is, we just want to balance the tree. So if your tree will be balanced properly, then searching will be optimized, definitely. Okay, so this is the so in the here the conclusion or is red black tree is the is the latest one nowadays in all this tree concept. So this associative container, if you talk about the, here I am talking about the G++. So in G++, if you see the policy of this map and set, this is using internally, they are using red black tree only. Okay, the concept here in map is, if you are inserting something into the map, okay, let's say you have inserted 1 2 3 4. So map is something, map is here I have explained this red black tree. Red black tree is common for both, okay. So map and set is associative container, okay. The principle, the properties of map and set is completely same. Now there is no difference, except that map is based on the key value concept and set is based on the value only, okay. These both are using the red black tree only. So in red black tree, if you see about the map, okay, so let's say you have inserted something 1 2 3 4, something like this. So something like is 1 2 1 4 3, something like this type of tree created, okay. So at every insertion, it will what this is doing in red black tree, at every insertion your tree will be balanced, at every deletion your tree will be balanced, okay. And in the red black tree, the searching will be optimized. So in red black tree, if you talk about this red black tree, the searching is, the complexity of searching is Bu of log n, okay. Log n is the number of element, log n is, so this is the, if your tree is completely balanced, right, so every if tree is completely balanced, that means it's something like as every node is having child nodes, like it could be 0 or 1 or 2, but it balanced properly, okay. So it could not like as your tree cannot like as a sequential, okay, it will balance. So in this case, in the case of map or set, your searching will be big O of log n, insertion again big O of log n, and deletion again big O of log n, okay. So map is the data structure which is giving you guarantee that insertion, deletion and searching will take big O of log n cycle. This is the advantage